Hello and welcome. This is the first ever No Soy Development Lecture. Today we're doing some work with Fourier Transforms. I wanted to make a video on the Fourier Transform just to explain it in more detail, because I think this is a very interesting subject actually, and let's not waste any time. Let's get right into it. So the Fourier Transform, which I've written here, is a transform which takes data which is sampled periodically in time or in any dimension. It can be sampled periodically along a spatial dimension as well. And it transforms it into the frequency domain. So if we have a time series hk, lowercase h, k here, then after completing the transform we have uppercase H, and this is data sampled periodically in time, and this data tells us about which frequency components are present in that data. So this is the Fourier transform. You may recognize this. We sum over all the elements of our input vector, if you want to think of this object as a vector, and we multiply by an imaginary number which has magnitude of 1, length of 1. And this imaginary number, e to the I something, is like a little clock wheel which goes around and around. In fact, we can even draw something to explain. So many of you, of course, will already know how imaginary numbers work. We have a real axis and an imaginary axis, and we have our number here, which I will just call C, and C is the exponential function of this thing. So we can just write I theta there, and then theta will be this. I'll write it like this. And the reason I've written it like that is this is our object theta here. So this thing. And as the numbers increase, let's see if I can get both on the screen at the same time. As the numbers increase in this sum here, no, I can't get both on the screen at the same time. As the numbers increase in this sum here, then this k value will increase, and this angle, the angle that we have in here, will continually step round with a fixed delta theta value. So to explain that in more detail, I hope I'm not labouring the point here. The delta theta value here, which corresponds to the delta k, well, delta k, the smallest delta k is 1. So the smallest change in k is 1. So we could do for, just to demonstrate, it's going to be, we ignore the I, 2 pi over big N. Big N, by the way, if it wasn't already obvious, is the length of our vector. It's the number of items in the input vector, and times that by small n, which is the index of our output vector, and then we will have k plus 1 will be the next k minus the current k. K cancels, delta k is 1, this is just delta k, so delta theta 2 pi n over n. What it means is the value in this exponential goes around like a clock with this increment of delta theta. So, for example, h1, the first, actually not the first, because we can have h0, but if you're counting from 0 the 1th, I guess is the best way to say that, not the 0th element, but the one after the 0th element, how does it go round this clock here? Think of this as a clock. How does it go round? Well, we've got this factor. I'll put n equals 1 here, and I can put a 1 there. So it goes round one whole rotation divided by n. Okay, so imagine we draw our clock, quote unquote clock. Again, it's not quite like a clock because 12 o'clock is here and the imaginary is here, and it goes that way instead of the way normal clock goes. And let's say if n equals 8, what do we have? Well, the first one will be here, 1. The next one is here, when we have an angle of 2 pi over 8. Writing's getting a bit small. Next one will be at positive I, and then we have another one here, and then another one here, and another one here, another one here, and finally here. So we have, this is supposed to be on a circle. It's not very well drawn. I'll just draw a little circle like this, and the clock goes round it does 8 different points in a cycle. And it will go round once. And because we can have k in the range 0 to n minus 1, which is not on the screen. So if k is 0, we will have this one here, because we will have e to the 0, which is 1. If we have n minus 1, and in this diagram, big N is 8, then this will be 7, right? So n minus 1 equals 7 in this example. So we have 7/8 of a rotation, which is that point there. Good. So that will come in handy later, actually, and we can go back to the first page. And indeed, if we introduce a constant w, which we define to be this thing, then we can make this look more like a matrix product. And we can think of this as a matrix product. So we have our vectors h, big H, little h at either side, and we are summing over k, and we have w to the power of n k. This is quite an interesting notation, because here it literally means w to the power of n times k. But we can write it like a matrix, and we can use n and k as the indices of that matrix as well. So you can imagine it like a matrix product. We have two vectors and a matrix of w values, so let's just pick one. So w01 is the same as w to the power 0.1, which is the same as this, w to the power of 0, which is 1, by the way. And there are a few interesting properties of this matrix. It's symmetric, which is fairly obvious. So wij is wji, so if this is equal to this, so it's symmetric around the diagonal. And as I was just pointing out up here, the elements of the matrix are just this constant to the power of the indices multiplied together. So just note here that I'm using w to mean two different things, the elements of the matrix and also just this constant here. So that's the constant there, e to the 2 pi I over n. I here is the square root of -1, I here is not the square root of -1, that's an index, just in case there was any confusion there. And yeah, there we go. So there's some other interesting things we can look at with this as well. In fact, I made a whole page of notes about this yesterday because I was doing some work on this. One thing that's maybe interesting is let's just write this out in long form. So we can do something like this. How do I want to do this? Yeah, this is what I want to do. All right, so let's just take a simple example. I don't want to write too much, so I'm just going to go for n is 4. So let's take an example for n is 4. So we have an input vector like this. With 4 items. Well, what does this matrix look like? Well, it looks like this. We have, W, sorry. We have, let's do it fairly big so it can be seen. W00, W01, W02, W03. You can see how this is going. W10, W20, W30. But what are these objects actually, what values do they actually have? So this one, we can do an intermediate step actually. We can have W0. I don't like that. That's how I wanted to do that. W0, W0, W0. Because for this first row, you always have a 0 in one of the indices, and anything multiplied by 0 will be 0. Same for this column. Let's do a few more here. So W11, well, 1 times 1 is 1. So you have W1. This one is W12, W13. So you have W squared, W cubed. 21, W22, W23. We'll just do them all. W31, W32, W33. And here we have W2, W4, W6, W3, W6, W9. And now we can write out what those values are. E to the, it's going to get a bit squished, so apologies for that in advance. 2 pi I over n times 0. E to the 2 pi I over n times 0, and the same here, and the same here as well. E to the 2 pi I over n 0. You're going to have the same. This one, e to the 2 pi I over n times 1. E to the 2 pi I over n times 2. E to the 2 pi I over n times 3. Let's just do the rest of these here. I will not write out the full thing. I'll just do this. To make it a bit quicker, I should have left some more room. We can extend this down here. We have 1, 1. This one's more interesting. This is e to the, this is the same as this one. It's symmetric about the diagonal. E to the 2 pi I over n times 2. E to the 2 pi I over n times 4. E to the 2 pi I over n times 6. E to the 2 pi I over, I'm going to leave this blank for a moment, times 3. I'm going to put the 8 in there. It's actually more clear if I, oh sorry, we're not doing 8, we're doing n is 4. 4. Let's change all of those actually. 4, 4, 4, 4. I hope it doesn't make it too unsightly to read. There's a reason why I want to do this. We'll just finish off. E to the 2 pi I over 4, 6. E to the 2 pi I over 4, 9. Now, do you see what's happening? Let's look at this row here. This one. The sequence is like this. E to the 2 pi I over 4 times 0, which is just 1. E to the 2 pi I over 4 times 1. E to the, I'm going to run out of space, 2 pi I over 4 times 2. And then finally, e to the 2 pi I over 4 times 3. So this is why I was talking about this clock earlier. So what is it? It's just these numbers. 1, I, minus 1, minus I. And the clock visits 4 points in this two-dimensional real imaginary space, complex space, and it starts here, it goes around to here, goes around to here, around to here, and then that's it. So it visits these 4 points, 1, 2, 3, 4. Now, how do we understand in more detail what this does as a Fourier transform? Well, imagine we have get some more room. Imagine we have some time series, and let's say it's looking something like this. That's supposed to be a cosine wave. This is supposed to be time. This is some y-axis. Let's actually call it h, because that's what it is. It's h of t. And imagine we sample this at 4 points. So let's say we sample it here, we sample it here, and here. Oh, that's 3. This will this be okay? Yes, it will be okay. I'll add another 2 here, and we won't count this n1. So you can say, okay, so this is h0, h1, h2, and h3. And we just ignore this one. We don't use this one. So there we go. Now, we've got 4 points that we've sampled here, which are these h values, and we are multiplying, because remember it's a sum, so we need more paper. Remember that it's a sum. We can even maybe write out the sum. So let's do h0 is very boring. So if I was to do h0, oh, this is a terrible piece of paper. In fact, I think are they all terrible? Yes, that one should be okay. We'll use this one. So h0 is this one's terrible as well. Let's get some different paper. Here's some different paper. So h0 is boring because you've got a sum like this. E to the 2 pi I. Let's say we'll keep n is 4, and we have times, and now this is n equals 0. So we have times 0 times k, h k. So this is always 1, right? So this is the same as this thing. it's still useful. I mean, this gives you what's called the DC component if you think about this in terms of electronics. So you're just adding up all the HK. It's like an average, except you don't have the divide by n factor. So you're adding. You'll see why it's an average when we come to do a different one. So when we have small n is 1, you'll see why it's an average. So you're literally just summing the h values. Now with our example above, you can see what this will be. We've got h0 is 1, h1 is 0, h2 is -1, there, and h3 is 0, so this is 0. So it's basically like an average. The average value is 0 in this case. Now if you have something that's not cosine, you have something that has a DC component, let's say cos of t plus, I'll call it like V0. Imagine it was, I don't know, some electronics thing, an electronic signal, an analog wave of some kind. Then you would be adding on V0 for each of these, and you'd end up with a H0 equals 4 V0. So it's not exactly an average, because the average would be V0, right? But you get the idea. By the way, when I drew this diagram, I chose to sample it at easy points. We could have added some phase here, and in fact you'll see that. So imagine we had some phase. Let's do sine as well, because that's got a phase relative to cosine. So sine would look like this. That's much better. H0, H1, 1, H2 and H3, -1 here. We'll come back to this. So going back to this page, let's how can I fit it all on the screen like this? There we go. Let's do H1. So H1, this is n equals 1. The sum from k equals 0 to, I could change this as well. Four minus 1 e to the 2 pi I over 4 times 1 for n equals 1. I'll write it in. Times k h k. So let's just write out the sum. So for k is 0, we have e to the 0 h0. For k is 1, we have e to the 2 pi I over 4 times h1 plus e to the 2 pi I over 4 times 2 h2 plus e to the 2 pi I over 4, not a very good 4, times 3 h3. So is it more obvious why it's an average now? We've got 1 times h0, which is just h0, plus this is just on the clock, this value here, I, because we have e to the pi by 2 I. So we have r plus I h1 plus minus 1 h2 minus I h3. Now if we look back at our sine or cosine, so let's say for cosine of t, we get this. We've got h1 will be 1, so we have 1 plus 0, because h1 is 0, minus, because this is the minus 1 here, and h2 will be minus 1. So minus 1 plus 0, which is equal to 1 plus 1 equals 2. So the clock was in phase with the cosine wave when it was going round. So as cosine, if you imagine the cosine being a rotation, a projection of a rotation, right? So if you have something here that rotates and you were to project that rotation onto a one-dimensional thing, then if this was rotating at a constant angular velocity, then what would you see? You would see this. You'd see this would actually be sine because of where I've started it, but the principle's the same. As this goes around, that's what you would see projected. I'm sure you're familiar with that anyway. And indeed, you also probably know this identity, which you can't see because it's gone off the edge of the screen. You have Euler's identity. Yeah? So we'll come back to this actually, and we can write it. We'll come back to this. We'll do sine now. Right, so h0 for sine is 0. So now we've got a 0 here. Now we have I times h1, which is 1. Then we have minus h2, which is 0. And then we have minus I h3, which is minus 1. So remember this is sine. Yep. So minus 1. So we get 2i at the end, which is interesting. So for cosine we got this value 2, and for sine we got 2i. So what this tells us is that the phase information is encoded as a phase rotation in this complex plane, because remember we're working with complex numbers. So if we shift our input signal by some amount, some constant amount, that will appear as a rotation in our complex space, the space of complex numbers that we're working with. Now, what about if we wanted to calculate the amplitude or the power spectral density after doing these Fourier transforms? Well, for cosine, the amplitude modulus of 2 is 2. And in fact, actually, imagine we were to shift our cosine signal by pi. Then h0 would have been minus 1. h1 would still be 0. h2 would be plus 1. So we would flip all the signs here, and we would have had minus 2 here. But the amplitude, when we take the modulus, still be 2. And the same here, the amplitude, we take the modulus of a complex number, which is the same as the, I'm sure you know, square root of the complex number conjugated times by itself. Complex conjugate is just minus, you exchange all i's for minus I. So we have minus I times I, which is 1, square root of 4, 2. It's the same. So all the phase information is contained in a rotation in complex space, which is quite interesting. Now, I said I was going to come back to this thing. I think we're out of paper on this one. There's only one sheet. Yeah, there it is. We need more paper. We're going back to our not so good paper then. And right, yes, so Hn sum over k equals 0 to n minus 1. This is really a terrible pen to be using on this paper. Fortunately, there are other pens available. We will use this one. Where was I? E to the 2 pi I over n dot k h of k. And we're interested in, let's expand this. Cosine 2 pi over n dot k. This doesn't make the math any easier, by the way. It's just to demonstrate the point that I want to make. Plus I sine 2 pi over n dot k h k. And now let's say h of k is, I'm not exactly sure where I'm going with this, but let's say a cos omega t plus b sine omega t, something like this. What do we get? We get this sum k equals 0, n minus 1, cos 2 pi over n k times by plus I sine all of this is still inside the sum, by the way. Now, will this help me to demonstrate what I wanted to demonstrate? Yes, I think it will. So let's... Yeah, what I really want though is I'm only interested in cases where omega is, it has the same, yeah, okay, right, so I need to just define something. So I need to say omega t, so let's say t is 0, 1, 2, 3, because before we had h sub k here. So to be strictly correct, we could put t sub k there, right? And we could have tk equals this, or we could do this. We could use maybe theta k. Because by doing this, we're really introducing too many degrees of freedom, right? Because we could we're only really interested in the case where omega t is the same frequency as this thing for now, right? Because of what I want to demonstrate. Otherwise it won't match up with these diagrams. So say t was 0, 1, 2, 3, 4, then we would want the argument, the frequency that this was occurring, to line up with, because so the index tk, do you see what I'm trying to say? The index tk, it should line up with this clock rotating round, right? So that they're going at the same rate. But it's a bit weird because you don't think of this in terms of, you think of a time series as something in time, but really here, I'll go back to my original page, we're only really interested in this sum, which just has an index k. So there's no real units. There's no units in this, right? It works for any units. So if this is measured along a dimension of time, the fact that once you put it in terms of, once you've sampled it and you've put it as a list of numbers, the units become irrelevant, right? So anyway, point being, k equals 0 to n minus 1, and we're going to have, I'm going to expand this part first, so we can put the a here, cos 2 pi over n dot k, and I'm going to rewrite the omega t like this, 2 pi over n dot n. So that's like the omega times by k, and this is like the tk, yeah? So if t was 0, 1, 2, 3, k is the same, 0, 1, 2, 3. So our omega is just this part. That's the omega I want to demonstrate what I'm going to demonstrate. Otherwise, maths becomes harder, basically. I have to use a new line. IA cos 2 pi over n dot k cos 2 pi over n, oops, that's a sign, sorry, n dot k, and then finally plus I b sine, and I'm just going to write it like this. You can probably see where this is going. So let's draw a diagram to help. I want to avoid doing lots of trig identities because you kind of get lost in doing trig identities and forget what you're really supposed to be doing. So sine, I need to draw it so it lines up. Wish me luck. Yeah. Kind of. So if we sum over this whole series, one thing here, one thing here, one thing here, one thing here, same as before. So if we have a sine and a cosine going around at the same rate, which these are, and we multiply them together and add them, we're always going to be multiplying by something that's 0. So these terms, this is the point that I originally wanted to get to, they go away because they're 0. Because at every point in time, we have a sine and a cosine, one of which is 0. So we're always going to multiply by something that's 0. Now, on the other hand, the cosine, let's imagine two cosines multiplied together. We would multiply 0 by 0, or 1 by 1, or 0 by 0, or minus 1 by minus 1. So for these parts, and the same for the sine square, we will always have a 1 or a 0. But so this is only 1 if k is 0 or 2, plus b, and this is only 1 if k equals 1 or 3. So I can write it in a more mathematically correct way. So we can have sum over k equals 0 and 2 of a plus sum over k equals 1 and 3 of b. So we get 2a plus 2b. Now, we finally get to the point that I wanted to make, because if you remember earlier, we were talking about, where is it? Somewhere, here it is. We were talking about what happens with the phase. In fact, I realise I've made a little mistake. It should be IB there. And there needs to be an I there. So we can see that if we adjust the phase by just changing the relative contribution of A or B, then all we're doing is rotating from something that's real to something that's imaginary, right? So A amount of a cosine and B amount of a sine, if we take the amplitude, we just get 2a minus 2b, 2a plus 2b. Sorry, this should be an I, and that should be square root. Expand it for a square. This will cancel, plus 4b square root. We can take out the 2. And that looks like a triangle. With a hypotenuse h equals square root of a square plus b square. So that's the point I wanted to make about this thing. So basically, if we add a change in phase, we're just shifting into the imaginary dimension, because all of our output is complex numbers. Okay, so that's quite interesting. We can go back. Did I fully make the point that I wanted to make about this matrix thing? Let's have a look. So we can bring back my page where I wrote out all these matrices. Yes, okay, so now let's consider the following line, this one here. The sequence now goes at twice the frequency we originally had, and the sequence here goes at 3 times the frequency. So all we're doing is we're taking an average. The first row, we just take an average with a phasor, a complex phasor that doesn't rotate. It's always 1. The next one, we take an average with a phasor that rotates by, if we have 4 points, it rotates along 4 points on the circle. If we have 8 points, it rotates along 8 points on the circle. If we have n points, then our phasor will rotate for h1. It rotates once, meaning it goes around, and it only goes around once. And the delta theta is 2 pi over n. So if we have n points, let's say we have n is, let's do, I'm not sure I can do an odd number, let's do 12. We've got 1, sorry, the 0, the number 5, can I fit 12? Yes, probably. I need maybe 1, 2, 3, 4. 2, 3, 4, yeah. So this is our phasor going around. That's delta theta here, yeah, the difference in this angle here. And you know, we could do it here as well. Delta theta. And this will be number 6, 7, 8, 9. How's that happened? This should have been 6. I've done 10 instead. It doesn't matter. This will do. We've done, instead of doing n is 12, we've done n is 10 instead. Okay, fine. Okay. And now what about, okay, so this is 1, h1. What about h2? Well, it rotates twice. And delta theta is 2 pi by n. So now we skip half of the points. So if I draw my circle again, we will visit point 0, but we will not visit point 1. So I'll just draw a circle. We visit point 2, but we do not visit point 3. We visit point 4, but we do not visit point 5. We visit point 6, but not 7. 8, but not 9. So delta theta is this, twice as big, and it goes around twice. So it will visit this point twice, right? Because the highest value of little n is n minus 1, which is, in this example, 10 minus 1 equals 9. So the largest angle that we go to is 2 times 2 pi over 10 times 9, which is 9/10 times 2 of 2 pi. 2 pi is 1 rotation, so this is 18/10 of 1 rotation. Now 18/10 of one rotation is more than one rotation. It's this amount of rotation. I'll use my other color. This amount of rotation. That much rotation. Yeah? And similarly, so you can see how this works. For 3, we rotate how much of a rotation is this? This is 3/4 of 2 pi. Now 3/4 of 2 pi is going all the way round to here, which is more than pi. Now that's quite interesting. So the higher frequencies, they are, so let's say this, e to the, what did I say, 3/4 of 2 pi is the same as e to the -1/4 of 2 pi. Right? Because if I go from here and rotate around to here, that's the same as going here and doing a negative rotation like that. So it turns out that once you go beyond halfway through your matrix, you start, your higher frequencies are actually equivalent to smaller negative frequencies. Okay, so, and even halfway for this one, we are rotating by pi every step. And if we rotate forward by pi, positively by pi, it's the same as rotating negatively by pi. So remember that this was our W matrix. The first row we are not rotating at all. The second row we're rotating by 1/4 of a rotation, which is the same as rotating a negative rotation, a negative frequency, 3/4. But we don't really think of it like that because it's not as intuitive. The following one is the highest frequency. It's both positive and negative because they're exactly equivalent. And then finally, we rotate by 3/4 of a rotation every step, or alternatively, by -1/4 of a rotation. So this is either a frequency of 3/4 or -1/4. Okay? And this is no frequency. So I can just show you some of the pages of notes I made while I was thinking about this yesterday. What would it be interesting to see? Maybe this. So this is along the lines of what I was thinking about, except I did it with 8. So this is the matrix. I've actually done it for a funny number. I've gone up to 8. But you can ignore the final row and column. And then it will be a power of 2, which is what you're used to seeing for Fourier transforms. It doesn't have to be, by the way, with this thing. It can be only the fast Fourier transform and such algorithms require it to be a power of 2. So the first row is all 1, that's DC. The next row we're rotating by 1/8 of a rotation every time. So it's a step of 2 times 2 pi I, is that? Yes, that's correct. Sorry, the first one is a step. That's what that arrow is about. Step of 2 pi I over n. So this means the final value. So 16 pi I. It's difficult to read on here because it's so small. But 16 pi I over 8 is the same as e to the 2 pi I. So this goes 1 rotation, This one goes 2 rotations, this one goes 3, this one goes 4, this one goes 5, which is the same as -1. This one goes 6, 7 rotations, etc. And the increments are a quarter pi, pi, three quarters pi, sorry, half pi, 3/4 pi, pi for each of these. And that's almost everything that I wanted to cover, really. I think thinking about this in this way makes the Fourier transform much more intuitive. So you understand what it's actually doing, what it's actually supposed to be measuring. Otherwise, it's just a big formula. It's quite confusing. There's some people on YouTube have done animations of this, which help to explain as well. But you can actually see it mathematically here. Yeah, so I think I'll end it there. I'm considering doing a whole series of videos, actually. Not sure on exactly what yet. I'm not too happy with I was trying to do live streams for coding. I don't think they're actually that good. So I might move on to doing more lecture stuff like this. This just happened to be something I was working on the other day that happened to come up. I thought was interesting. I thought I'd share it. Let me know if you found this interesting. We can do more of this kind of thing. I'm probably going to move over to doing physics lectures fairly soon as well. So look out for those. Those should be good. We'll do some ray tracing, I think, as soon as I finally get myself sorted and finish my ray tracing program. We'll do a lecture on ray tracing. That will be quite interesting. Okay,